Okay, in today's video, I'm going to be going over an explanation of elastic collisions and momentum. Of course, in a previous video, I went over an explanation of momentum and inelastic collisions, but today's video is fun with elastic collision. Now, what is the difference between elastic and inelastic collisions? Well, in an elastic collision, the masses do not stick together. They bounce off of each other. For an elastic collision, then the kinetic energy is conserved. I would say that's the big difference between elastic and inelastic. Inelastic kinetic energy is not conserved, but in this kind, perfectly elastic collisions, kinetic energy is conserved. And of course, in both, momentum is conserved. That's very important to remember. Now, most collisions we deal with in real life are collisions where the kinetic energy, there is some energy lost. So most collisions are inelastic. But there are some typical elastic collisions that we can use to talk about, and one of those is the collision of the gases in an ideal gas, the particles in an ideal gas. That can be modeled as an elastic collision. Also, the collision of billiard balls when you're playing pool, you're playing billiards, those collisions can be modeled as elastic, and also the collision of the metal balls in a Newton's cradle. And perhaps you've seen one of the devices, looks like this. The collision of those objects can be modeled as an elastic collision. Okay, so let's just say a little bit more about what we mean by conservation of energy and conservation of momentum. That means that the initial kinetic energy of the system is equal to the final kinetic energy, which means we can add up the kinetic energies of the objects before the collision and set that equal to the kinetic energy of the objects after the collision. And we can do the same thing with the momenta. The momentum of the initial momentum of the system before the collision is going to be equal to the momentum of the system after the collision. Initial equals final, which means that we can sum up the momenta of the objects before the collision and set that equal to the momenta of the objects after the collision, initial and final. Now, usually the first thing you're asked to do, of course, is to find the final velocities of the two objects. The final velocity of mass number 1 and the final velocity of mass number 2. Now we have two different, not always different, but we have two final velocities because the objects don't stick together. That means we need two equations to solve for two different variables. We just happen to have two equations, the kinetic energy equation and the momentum equation, and we can use these two equations to come up with the final velocity of mass number 1 and the final velocity of mass number 2. Now the derivation of those two equations is a little complicated but kind of long, so I'm not going to go through the whole thing in this video. I'm just going to give you the equations. So simply, here's the equation we use to find the final velocity of mass number 1, and here's the equation we use to find the final velocity of mass number 2. They're not that complicated. It's usually just adding and subtracting the masses, multiplying times the velocities. So it's not too complicated. And I don't think your teacher will ask you to memorize those. Just maybe need a little practice. Again, making sure you get those kind of order of operations done correctly. Now, sometimes I just want to say this is the equation for the final velocity of mass number 2. Sometimes you'll see a negative sign here or a minus sign here, and then these two terms will be switched, 1 minus 2. It's the same thing, we get the same answer. I think usually you see it with plus signs and 2 minus 1, but you'll get the same answer, and this is the most common form, so I just used that, and I like to be consistent kind of with my pluses and all that kind of stuff. Okay, so those are the two equations that you use. Now, in some next videos, I'm going to go over some specific examples where we'll do the calculations to find the initial velocity, the final velocity of mass number 1 and the final velocity of mass number 2. We're not going to do that here. What I want to do now is to go over 4 different conceptual examples, kind of extreme cases that I hope will give you kind of a conceptual understanding for elastic collisions. And this is the first one, case number 1. Mass 1 collides with an object of equal mass, mass 2. So M1 and M2 have the same mass, and M2 is at rest. M1 is moving. The initial velocity of mass number 2 is 0. This is before the collision, and of course, maybe you can think about what will happen after the collision when they have equal masses, one's at rest and the other is moving. When that occurs, basically they just switch their velocities. So after the collision, because they have equal masses, now the final velocity of mass number 1 is 0, and mass number 2's final velocity is equal to the initial velocity of mass number 1. So we can just sum that up by saying that the final velocity of mass number 1 is 0, and the final velocity of mass number 2 is equal to the initial velocity of mass number 1. Now that is only the case that these two velocities are equal to each other when the masses are equal. All right? Now, case number 2. Now we have two objects. They have the same mass, they have the same speed, but they're moving in opposite directions. They're moving towards each other and they're going to collide. Now they're not going to stick to each other because this is an elastic collision, and therefore what they do, they just bounce off of each other and move away with the same velocities in the opposite direction. Same masses, same speeds, opposite directions. They collide, bounce off of each other, and move away from each other with the same velocities. And we can kind of say it this way, that the final velocity of mass number 1 is equal to the initial velocity of mass number 2, and the final velocity of mass number 2 is equal to the initial velocity of mass number 1. But what do? They bounce off each other, move away, and all the velocities or the speeds are all the same, but the directions, of course, are a little different. Okay? Here is case number 3. Now, this is a little different. 3 and 4 are a little different. It's a little bit more interesting, maybe. We have a very massive object, M1, and a much less massive object, M2. This one's moving, and this one is at rest. Now, this is kind of an extreme case, as I said, and this is where the mass of M1 is much greater, maybe 10, 100, or even 1,000 times greater than the mass of M2. And when those two objects collide, what happens is that M1 continues to move off with the same velocity. Its initial and final velocities are the same, and the velocity of M number 2, which was initially at rest, its final velocity is 2 times the initial velocity of mass number 1. So I wrote that down right here. The final velocity of mass number 1 is equal to its initial velocity. This velocity doesn't change. And this one, which was at rest, it moves off. Its final velocity of mass number 2 is 2 times the initial velocity of mass number 1. Now, the fact that M1 doesn't change its velocity, and the fact that the velocity of M number 2 is twice the velocity of mass number 1 only occurs when there's a very large difference in the mass of the two objects. And like I said, 10, 100, maybe 1,000 times difference. Okay? The greater the difference, the closer it gets to be that this has its initial velocity the same as the final, and this is 2 times the initial velocity of mass number 1. Okay, the last one of these is now we have mass 1 and mass 2 again. Mass 2 this time has a much larger velocity than mass 1, maybe 10, 100, 1,000 times bigger. And M2 is at rest, M1 is moving. Now this is much larger mass, so it's almost like it's a wall. So this one just bounces off of it and moves away in the opposite direction with the same speed. Okay? So after the collision, M2 is still at rest, and M1 has the same speed but the opposite direction. Again, this only occurs, this 0 and this the same speed, opposite direction, when this object is much more massive than this object. Okay? So we can summarize that by saying that the final velocity of mass 1 is equal to the same velocity but opposite direction of mass 1. Doesn't change its speed, same speed, opposite velocity. And mass number 2 remains at rest. Okay? Remains at rest. Okay, so there you go. I went over kind of an explanation of what elastic collisions are. We talked about how momentum and kinetic energy are conserved for elastic collisions. I gave you the equations, and then I went over some cases for kind of a conceptual understanding of elastic collisions. Okay, hope you found the video helpful. If you did, please do all the following 4 things. Subscribe to my channel, get all my excellent physics, chemistry, and math videos. Give me a thumbs up for this video. Leave me a nice positive comment in the comment section below. And don't forget, sharing is caring. Share this video with all of your friends. Show them how much you care. Thanks for watching. We'll see you in the next video.